Hello everyone, welcome to CSP channel, Learn Easy Way of Physics. Watch my previous videos. If you are not watching my previous videos, you cannot understand present videos. So you can watch my previous videos, subscribe and tap the bell icon for notifications. Today we are going to discuss about velocity of wave on a string. Velocity of wave on a string. The velocity of a wave on a string depends on elastic and inertia property. Elastic and inertia property. Inertia property. When the string is disturbed, velocity of wave on a string depends on elastic and inertia property. When the string is disturbed, it exerts or extra force acting on the neighboring because elastic property. The neighboring is a response to that force. That response depends on inertia property. So the elastic in nature in the string, it is measured by tension P, and the inertia by its measure mass per unit length. When the string is vibrating, the wave is traveling along the x direction. This is positive x direction, and the displacement is in the y direction. Here is, let us consider the length of this element is delta L. Distance of the mean position is x naught. This element is taken outside like this. Where is the wave is traveling? The wave is traveling in the forward direction. That means it is moving along the positive x direction. Hence the wave displacement function is f of t minus x by v. Already we discussed this equation. Now the element is taken outside like this. Here is tension. This is also tension in the string. Here 0 means O, radius capital R, here is capital R. The length of the element is considered, that is delta L. Here is AB. AB is a length of the string, length of the element. Here is which makes an angle of theta. Here is also angle theta. Here is at center theta. Here is also theta. AB is a element at two ends, at left and right side. AB is one of the elements. It is pulled by a string at left and right side. Hence the two components are T sine theta. Here is also T sine theta. Here is also T sine theta. There are two components. They are vertical components. What is the direction of these components? These two components directed towards downward. Here is when the resultant force of this element, always directed towards downward. Hence, which is acting on the resultant force on this element, the direction is in the downward direction. Here is the resultant force F4 equal to T sine theta plus T sine theta. F4 equal to 2T sine theta. Here is the length of the element is considered delta L. So it is small. Hence the theta is also will be small. Here sine theta is a negation theta. F4 equal to 2T theta. Here is the resultant force is acting towards downward, that means that is towards its center. The force which is acts towards the center, we know that already we discussed previously about centripetal force. What is the centripetal force formula? That is centripetal force formula F equal to mv square by r. So according to centripetal force, F4 is equal to, here is mv square by r. According to that force, the resultant force is given by Fr equal to mv square by r. But linear density of this element, that means that is the linear density of this string, mu is equals to m by, here is the smaller length, the element of the length is considered delta L. Actually the linear density is measured by mass per unit length, we know that. That is mu equal to m by delta L. So we need to take mass, m is equals to mu into delta L. But the delta L is equal to capital R, means that is a radius 2 theta. Both angles are there, no? The total angle is taken here 2 theta. So you can substitute here. Mass m is equals to mu into delta L is r 2 theta. 2 theta. Then we can substitute in the place of m, Fr equal to m is mu r 2 theta is divided by r here. So v square also there, v square, here is also v square. Both small m we substituted in the place of delta L. After that the small m is substituted in the place of small m here. So finally the resultant force is given by Fr equal to mu r into 2 theta v square by r. So this formula is taken from centripetal force, because of here is the resultant force is directed towards downward, no? So that's why the resultant force is taken as from centripetal force Fr equal to mv square by r. Again, this is first equation, this is first equation, this is second equation. Equating both equations, equating equation 1 and 2. So the first equation is here 2t theta equal to mu r 2 theta v square is divided by r. Here r get cancelled, 2 theta, here is also 2 theta get cancelled. The remaining t equal to mu v square. Here v square is equals to t by mu. V equal to under root t by mu. This is the velocity of wave on a string or speed of wave on a string. V equal to under root t by mu. Write these points. Write these points. Here where T is tension in the string, mu is linear density, V is velocity of a wave or speed of wave. If the direction is indicated or represented, it is considered velocity. If only the magnitude is considered, it's considered as speed. So one example problem here. A linear density of string. A linear density of a string is 2 grams per centimeter. 2 grams per centimeter. When the wave is traveling, along the string, the time taken to travel through a distance 50 centimeters, through a distance 50 centimeters along the string, take G equal to 10 meter per second square. Here is one of the diagram is given. The supports are like this. Here is one of the pulley. The wave pulse is traveling like this. Here is the wave pulse. After vibrating, the pulse can be produced. So the wave pulse is traveling along the string, That's why, so the wave pulse is traveling and it is above surface of the pulley. Here is mass is 2 kg is attached to the string. This is the problem. A linear density of a string is 2 grams per centimeters when the wave is traveling. When the wave pulse, here is a wave or wave pulse is traveling along the string, the time taken to travel through a distance 50 centimeters along the string. Take G is equals to 10 meter per second square. What we should calculate from this problem? So we have to calculate here the time taken. What is the time taken to travel the pulse along the string? But the string is passing through over on the surface of the pulley. But some of the weight is attached to that string. That is, the mass is 2 kg here, 2 kg mass. So what are the values are given? Linear density, that is mu. Mu equal to 2 grams per centimeters. You should convert 2 into 10 power minus 3 kilograms per centimeters, that is 10 power minus 2 meters. Finally 2 into 10 power minus 3 into 10 power 2, so that is 2 into 10 power minus 1, 10 power minus 1 kilograms per meter. That is the linear density. Now after that, here length is given 50 centimeters. The length is given here is 50 centimeters. Length L is equals to 50 centimeters, means that is equals to, converting meters, 50 into 10 power minus 2 meters. Now we should find out the first of all speed of this wave pulse. V equal to under root of T by mu. T by mu. We know the value of mu, but the tension is there or not there here? A linear density. Tension we have to calculate it. The weight of the body is given. It is hanging with the string, that is 2 kg. Right? The tension T equal to, here tension T is equals to mg. So what is the mass? 2 kg. 2 into 10 here 20. mg, that is 2 into 10, 20 newtons. Kilograms meter per second square or 20 newtons. So we know the value of T and mu. The mu value is 2 into 10 power minus 1 or 0.2. So substituting. here V equal to, what is capital T? 20 newtons. And the root 20 is divided by mu value is 2 into 10 power minus 1. That is here 200 is divided by 2. That is 100, no? Here is 100. That is equal to 100. Finally, 10 meter per second its speed of the pulse. First we have to calculate the speed. So what is the value of speed here? V equal to 10 meter per seconds. Then after that we have to find out the time taken to travel through a distance is 50 centimeters. The distance is given already, that is 50 centimeters. After converting, it is 50 into 10 power minus 2 meters. So let us go to find out, calculate time to travel the wave pulse on a string. Speed V equal to distance by time, but the time taken T is equals to S by V. Here is what is S? S is given, no, 50 into 10 power minus 2 is divided by V. V is 10. Okay, 0, 0 cancel here. Finally 5 into 10 power minus 2 seconds. That is 0.05 seconds. Write the problem. Next problem is example 2. Here is next problem is based on the speed formula. A transverse wave is traveling with the speed 20 meter per seconds. Okay, under tension of the string, is 10 newtons. Then what tension is required? Tension is required under the speed of transverse wave 30 meter per seconds. 30 meter per seconds. A transverse wave is traveling with the speed 20 meter per seconds under tension of the string is 10 newtons. Then what tension is required under the speed of transverse wave 30 meter per seconds? So now here what are the values are given in the question? You can identify first. 10 newtons is given. A transverse wave is traveling with the speed 20 meter per second. So let us consider the speed of the transverse wave along the string is given, that is V1 equal to 20 meter per seconds. Under the tension, so what is the tension? Tension is equals to, here is 10 newtons. So then what tension is required? That means we don't know about the tension. So at which speed? That is the speed V2 is equal to 30 meter per seconds. Then we have to find out the tension T2 here. from the speed formula, speed of the wave, v is equal to under root t by mu. So here is v which is directly proportional to root t when 1 by mu is constant. 1 by root mu is constant. Here is v1. This relation can be written as v1 by t1 equal to root t1 is divided by root t2. Then we have to find out t2, no? So here is t1 square by t2 square. T1, that means that is t1 by t2 is equals to v1 square by v2 square after squaring on both sides. That is t1 by t2 equal to v1 square by v2 square. t2 is divided by t1 equals to v2 square by, here is v1 square. We need to find out t2. t2 equal to v2 square by v1 square into t1. So what is v2 here? v2 is 30. That means 30 into 30 by v1. v1 is 20. 20 into 20 into, what is t1 here? t1 is 10. Here 0, 0 cancel and 30 is there, no? 0, 0 cancel, 33 is 90. Here is 2 ones are 2 15s are 15 threes 45. 45 by 2. 45 by 2 means 2 2s are 4 and 2 2s are 2 5. 22.5 newtons. Here is T2 equal to V2 square by V1 square into T1. So what is V2? V2 value is given, no? 30 meter per seconds. V2 square here 30 into 30 is divided by V1. What is V1? V1 is 20 meter per seconds. Here is 2 times written 20 into 20. But T1, what is the tension? 10 newtons. Okay, we have to find out the tension, second tension, that is T2. We don't know how much it is. So that is tension is here substituted. 10, 0, 0 cancel, here 0, 0 cancel, 2 ones, 2 15s, 15 threes, 45, the remaining value is here 2, 45 by 2, that is 22.5 newtons. Is it clear? Topic is power transmitted along the string. Power transmitted along the string by sine wave. This is a rigid support. A wave is traveling like this. It is moving along the positive x direction. Here is the particle, the minimum vibration of that particle at time t equal to 0. Let us consider one of the element, its mass is dm, its length is dx. When the vibrating particle is associated with a kinetic energy, then that kinetic energy K equal to half mv square. So when considered the small element along the path of the wave, its mass is dm, its length is dx. Hence the kinetic energy of that element K equal to half dm v square. Here K means here dk, change in kinetic energy of that element along the path. Its kinetic energy is given by half dm v square. So after that we know that the velocity, wave velocity formula v equal to a omega cos kx minus omega t. So we can substitute in the place of v, that is half dm v square. V square means here a square omega square cos square kx minus omega t. dm a square omega square cos square kx minus omega t. Here dm, according to the linear density of the string, linear density of the string. When string is vibrated, the wave is transmitted along the string, and above the surface the element is considered, its length is dx, and the vibrations of that particles in that elements, its kinetic energy is taken, that is of dmv square, but the wave velocity takes place a omega cos of kx minus omega t. After substituted in the place of v, then of dm a square omega square cos square of kx minus omega t. Next, according to the linear density of the string, that is mu is equals to mass per unit length, but here is mass is the mass of the element. Here considered dm by length. Here length is dx. We need to take dm equal to mu dx. Substituting in this formula dk, which is equal to of, what is dm? Here is dm, no? What is dm here? Mu dx. Mu dx a square omega square cos square. Here is kx minus omega t. Cos square of kx minus omega t. Here that is equals to, write in order, of mu a square omega square, here cos square kx minus omega t into dx. This is the kinetic energy of that element. Now here dk, integrating on both sides, integration dk equal to integration of mu a square omega square cos square kx minus omega t dx. I have written like this. Now integration dk means, that is k equal to half into mu a square omega square. They are the constants. Write in outside the integration. The limits are 0 to lambda here. Mu a square omega square integrating 0 to lambda cos square kx minus omega t dx. Minus omega square minus, here is of mu a square omega square integration 0 to lambda. These are the limits. Cos square of kx minus omega t into dx. Here is at time t equal to 0, no? Time t equal to 0. Here time t is equals to 0, we can write a kx minus omega t. This will be 0. This will be 0 means we have to write kx dx here. Kx dx. Here is also kx dx. Kx dx. Because of the vibration of the particle is minimum. It comes rest position at the time taken t equal to 0. That's why here is the t value substituted at the place of t. This term will be 0. The remaining part is written here, kx cos square kx dx. Cos square kx dx. But cos square kx equal to 1 by 2 of 1 plus 2 cos 2kx. 1 by 2 of 1 plus cos 2kx. Cos 2kx. Now substituting kinetic energy k equal to of mu a square omega square integration 0 to lambda. Here is cos square kx. Cos square kx is this of 1 plus cos 2kx dx equal to of mu a square omega square. After integration with the limits, I am writing here lambda by 2 plus 2 sine k lambda by 2 here. So K lambda is a angle of sine. That's why, so here K lambda is considered, the angle is 0 degree, completely it will be 0. The remaining part is 1 by 2 mu a square omega square. This is the kinetic energy into lambda by 2. So finally 1 by 4 mu a square omega square. This is the kinetic energy. The kinetic energy is equal to 1 by 4 into mu a square omega square. So this is the kinetic energy of the element where it is considered along the path of wave, but the wave is moving along the string. Now here is potential energy of that element. U is equals to same as that of kinetic energy. U equal to 1 by 4 mu a square omega square. Mu a square omega square. Here is lambda is also there, no? Lambda. Here is also lambda. 1 by 4 mu a square omega square lambda. Here total energy, that is kinetic energy plus potential energy, that is equals to here 1 by 2 mu a square omega square lambda, because of 1 by 4 mu a square omega square lambda plus 1 by 4 mu a square omega square lambda. 2 ones, 2 twos get cancelled. So after cancellation, then 1 by 2 mu a square omega square lambda. This is the total energy. The total energy of that element. Here, power transmitted along the string by sine wave. So we have to find out the power transmitted along the string. But the power P equal to, here the total energy by total time. Work done upon unit time is called power. We know that upon time. So here is the total energy upon the time, total time, that is called as power. That is equal to total energy. Here total energy is of mu a square omega square lambda is divided by capital D. That is equals to half into mu a square omega square lambda by T. Since here we know that V is equals to L lambda, but V equal to here is lambda by T. So the wave velocity V equal to lambda by T already discussed in the previous class. Now here where the lambda by T we can substitute the V velocity, that is of mu a square omega square V. This is power. This is power of the element which is moving along the path of the wave by sine wave. Now intensity of the wave. Okay, the next topic is intensity of wave on a string. Intensity of wave. Intensity of wave on a string. Intensity I is equals to power by area of cross section. We know the formula power P equal to 1 by 2 mu a square omega square V. That can substitute in the place of V. That is equals to, what is power of mu a square omega square V is divided by A. Since here we know that the linear density of the string mu equal to mass per length. Since here 1 by 2 mu, in the place of mu you can substitute M by L. M by L a square omega square V is divided by A. Here is half into M a square omega square V is divided by AN. Here since here that is equals to half into AN. AN is nothing but here AL, area into length, that is volume. V equal to, here AL is equals to V. V is nothing but here volume. Here is volume. Now half into m a square omega square, here V is divided by V. Here is V, this is small v, velocity, this is V, volume. Now that is equals to half m a square omega square V. Here m by V. I am writing here m by V into a square omega square velocity V. M by V is nothing but density, mass per volume. That is half into rho a square omega square V, where rho is the density, a is area of cross section, omega is angular velocity, V is velocity of the wave. So finally the intensity of wave on a string is I equal to 1 by 2 rho a square omega square V. So this is the equation for intensity of wave on a string. Thank you very much.